So hello guys, welcome back on my channel once again. So this is Amit Brute and you're watching Mystery Wali Chemistry. Okay. So in our last video, we discussed about ozonolysis of reaction, how that ozonolysis reaction occurs. Okay. So in today's video, we're going to discuss mechanism of this ozonolysis reaction, and again I'm going to repeat some tricks regarding ozonolysis reaction. Okay. So stay with us. Ozonolysis reaction, that is about mechanism of this reaction. Mechanism of ozonolysis. Mechanism of ozonolysis or ozonolysis. Okay, so let's recall that same reaction. What is that ozonolysis reaction? As you know that it's a reaction of unsaturated hydrocarbon. So let us have one example. CH2, then double bond CH2. Okay, right? It's alkene. This alkene is called ethene. Yes, good, very good. Or its common name is ethylene also. Now this reaction occurs in presence of ozone, and in presence of solvent. The common used solvent for this ozonolysis is the carbon tetrachloride. It is the inert solvent. Okay. Now addition always occurs across carbon-carbon double bond. So you get this CH2, you get hut-like structure, right? Yes. You get hut-like structure. This one molecule of ozone can break two covalent bonds. So both these carbon-carbon bonds undergo cleavage, resulting this intermediate compound, and we call this intermediate compound as a ozonide. So it is a ozonide of ethene or ethylene. So it becomes ethylene ozonide. Okay, and this on either oxidative or reductive cleavage. So it's a reductive cleavage. You can also use your oxidizing agent like hydrogen peroxide or any other oxidizing agent. So that cleavage takes place like this, giving, in this case, we'll get two molecules of formaldehyde because our reactant is a symmetrical alkene, and we'll get this CH2 double bond. Sorry, we'll get HC double bond O and H. That is CH2O. Means we'll get two molecules of this compound is called formaldehyde. So it is a formaldehyde, and plus we'll get a molecule of zinc hydroxide. That is ZnOH twice. Okay. Yes. Now it's an overall reaction, and if you see the mechanism of this reaction, then when ozone molecule gets added across this carbon-carbon double bond, or when it gets added on alkene, then before giving this intermediate compound called ozonide, you'll get one more intermediate compound, and that intermediate compound is called molozonide. That is known as molozonide. Okay, that is called molozonide. So how this and again this molozonide on further rearrangement reaction gives rise to this ozonide, and that on any kind of cleavage gives carbonyl compound. Okay, so it's the reaction. So in other words, we can write the same reaction in a general fashion like alkene or even alkyne also. That is any unsaturated hydrocarbon. So alkene on a reaction with ozone in presence of CCl4. First of all, it gives us what intermediate compound that is called molozonide, and this molozonide on further rearrangement reaction gives ozonide, and this ozonide on any kind of decomposition, either oxidative or reductive, it gives us what carbonyl compounds, which may be aldehydes or ketones or carboxylic acids or anhydrides, and in some cases that ozonide on decomposition, it also gives us what alcohols, maybe primary or secondary alcohols, right? So it's an overall reaction. Now let's see actual mechanism of this reaction, how this ozone molecule gets added across carbon-carbon double bond of alkene. Okay, yes. Suppose, okay, let's have general representation of alkene. C double bond C, then dash, and then dash, dash, and dash. So it's alkene. Okay, Alkenes are the compound which contains carbon-carbon double bond, at least one carbon-carbon double bond in their molecule. Here what happens? Ozone molecule, ozone. We write formula of ozone as a O3. Okay. Now we are going to use actually Lewis structure of ozone, and all of you are I think familiar with this Lewis structure. With the Lewis structure of what? Some molecules. So the Lewis structure of this ozone molecule is like this: oxygen, then oxygen, and then oxygen. Two of the oxygen are doubly bonded with each other. Okay, so these two are doubly bonded with each other, and this oxygen is a triply bonded. Okay, it is means the valence of this oxygen, it is 3, and we know that oxygen which is doubly bonded always contains two unshared electron pairs. Okay, so as here the valence of oxygen becomes 3, meaning it carries only one lone pair, and its valence gets increased or due to absence of that one unshared electron pair, it carries positive charge, and singly bonded oxygen always carry 3 unshared electron pair. Okay, basically oxygen contains how many lone pair? 2 lone pairs. So here in this case you can see that it carries 3 lone pair. So because of presence of one extra electron pair, this carries negative charge. Okay, so it's the Lewis structure of what? Ozone molecule. If you know it's the resonating structure, then that will be like this: oxygen, then double bond, oxygen, then single bond, oxygen. Okay, double bond is not property of any two particular oxygen atom, so we can also change the position of double bond. Positive charge on this central oxygen remains as it is. This doubly bonded oxygen carries 2 lone pair, and singly bonded oxygen carries 3 lone pair. And because of presence of that extra electron pair, that carries negative charge. So these two are the resonating structures of what? Ozone. So to use any one of these. Okay, so let us use this resonating structure of ozone. So let me clear it. So here is our ozone molecule: oxygen, then singly bonded oxygen, then doubly bonded oxygen. Okay, it carries two lone pairs, it carries only one lone pair, positive charge, positive charge. It carries negative charge because of presence of one extra electron pair, extra electron pair. Okay, so it is the Lewis structure of what? Ozone, and here is our alkene. Here what happens? One of the electron pair, extra electron pair, oxygen gives this its one extra electron pair to this carbon atom, okay. But remember, when we shift this electron pair on this carbon, then this oxygen is going to form bond with this carbon, so the balance of this carbon becomes 5, and we know that the valence of carbon is always 4. So at the same time, here what happens? This pi electron pair is given to this oxygen atom, so that here is a formation of bond between this carbon and oxygen. But again, the valence of this O becomes 3. So therefore, at the same time, this pi electron pair is shifted on that oxygen, utilizing its positive charge. Got it? Yes. So first of all, we look at structure like this. It's a carbon, that is this carbon, and these two dash indicates two valences of this carbon. Then now double bond converts into single bond, single bond. Again, these two dash indicates two valences of carbon, two valences of carbon. Right? Here is a formation of new bond between this carbon and oxygen of ozone. Here is a single bond, singly bonded oxygen. Then this double bond converts into single bond. So here is a third oxygen of ozone. Okay, and here is a formation of new bond. Right. So here, if you check the valence of three oxygen atom, then it is 2. Meaning all these three oxygen atom now carries how many lone pair? 2 lone pair each. 2 unshared electron pairs are present on this oxygen atom. Okay, got it? Yes. So it's addition reaction. It's a addition reaction. In the next step, so now this compound is known as that compound called molozonide. So it is our molozonide. Now this molozonide, on further rearrangement reaction, it gives us what? That intermediate compound that is called ozonide. So here what happens? Here this one of the electron pair of these two, or of this oxygen, or even of this oxygen. So I'm using this oxygen. So I'm giving this unshared electron pair between this carbon and oxygen. So that here is a formation of what? double bond, right? But the valence of this carbon becomes pi, correct? So at the same time here, this carbon-carbon bond undergo cleavage, and this electron pair is given between this carbon and oxygen. Okay, carbon and oxygen. And now what happens? This electron pair, that is this OO electron pair, is given to this oxygen. Is given to this oxygen. So that this oxygen now carries one extra electron pair, and because of presence of one extra electron pair, now this oxygen carry negative charge. Okay, and because of three valencies, or because of absence of one lone pair, because we're shifting this electron pair in between carbon and oxygen, so because of absence of one electron pair, now this oxygen, or because of three valence of this oxygen, now it carries positive charge, right? So here actually, after such type of what shifting of electron pair, this molozonide is going to be what, or it is fragmented, we can say fragmented. So it gives us two fragments. Okay, we get this as a one fragment and this as a other fragment. So the two fragments of this molozonide are like this. It's a carbon, then here is a formation of pi bond, so double bond O, double bond O. It is singly bonded with this oxygen, single bond O. Because of presence of an extra electron pair, it carry negative charge, and because of absence of one lone pair, or because of its three valency, it carry only one lone pair, and hence it carry positive charge. Okay, we'll get this as a one fragment, and we'll get one more fragment from this side. So that second fragment is like this: carbon, double bond O, then dash, and then dash. Carbon, double bond O, and these two dash indicates two valencies of what, that carbon, remaining two valencies of that carbon. Now this fragment is a carbonyl fragment. You know that, that is C double bond O group is called carbonyl group. So that is the one fragment is a carbonyl fragment, and the other fragment is a carbonyl along with this oxygen, and O is having negative charge, and negative charge oxygen is generally there as an oxide ion. So we can call this fragment as a carbonyl oxide. So it is a carbonyl oxide. So these two are the fragments, okay, of molozonide, right? Got it? Yes. So in next step, what happens? These two fragments, they rejoin together, giving that ozonide, okay, of the reaction. So let's write that two fragments of molozonide like this. It's a carbon. Okay, I'm taking first of all that carbonyl fragment, then dash, then dash. Two dash indicates two valences of carbon. Then here is a double bond O, double bond O, correct? So double bond O, right? Got it? Yes. Then that is second fragment. So C. Okay, let's have this fragment first. This fragment. Okay. So we will take you can also take this fragment in opposite manner. So dash O with negative charge. With negative charge. Why does it have negative charge? Yes, because of presence of one extra electron pair, right? And it carries only one lone pair, so it carries positive charge. Positive charge. Got it? Yes. Now, second fragment is the carbonyl fragment. I'm writing that carbonyl fragment like this: C, then dash, and here is a double bond, O, doubly bonded oxygen always carry two lone pairs. So these are the two lone pairs of this second fragment called carbonyl fragment, right? Yes. So here what happens? See, here transfer of electron takes place like this. This electron pair, it is utilized to neutralize the positive charge present on this oxygen. So this positive charge gets neutralized, and at the same time, this negative charge, okay, which indicates presence of an extra electron pair. So this one extra electron pair of this oxygen is given to that carbon, and then this electron pair is shifted in between this carbon and oxygen, so that here is a formation of new carbon oxygen bond, so giving this type of compound: carbon, then dash. So these two are the two valencies, two represents two valencies of carbon. Now this double bond converts into single bond. So here is singly bonded oxygen. Then again you will get again here is a one more oxygen. Then single bond oxygen, formation of new sigma bond or single covalent bond. Then double bond converts into single bond. So here is single bond carbon, single bond carbon. Then two dash. These two are the two valences of that carbon, and here is a formation of new carbon oxygen bond giving, yes, hut-like structure, right? Now this hut-like structure is known as what? Correct. It is called ozonide. It is called ozonide. And in next step, you know that this ozonide undergo any kind of cleavage, oxidative or reductive cleavage. So normally, in most of the cases, we use reductive cleavage. So I'm using here zinc as a mild reducing agent. Okay, you can also use dimethyl sulfide or even that triphenyl phosphine as a reducing agent, which are mild reducing agents. So this ozonide undergo cleavage like this. Okay, it undergo cleavage like this, right? So what happens? We'll get dash C double bond O C. This will get dash C dash double bond O. Now this group is a carbonyl group. It's a C double bond O. This CO bond undergo complete cleavage. This OO bond undergo complete cleavage, right? And here again formation of one extra bond between this carbon and oxygen. This CO bond undergo complete cleavage. So you'll get one more unit of what? Same. Means overall you will get two units of this. You get two carbonyl units. Means you will get two carbonyl compounds. Okay, and this third oxygen it couples with this zinc, giving ZnO, that is zinc oxide, which on decomposition by water gives us what? Yes, that zinc hydroxide, ZnOH twice, means zinc hydroxide. So it's a mechanism of this reaction called ozonolysis reaction. Yes, is it clear? So very simple mechanism. Here we use one of the Lewis structure of what? Ozone, and that addition of ozone takes place like this, resulting first of all a molozonide. So it is a molozonide or a mole ozonide, and mole ozonide on fragmentation gives two fragments. The one is carbonyl oxide, so it's a carbonyl oxide, and the other fragment is a carbonyl group, and that again undergo what? That undergo a rearrangement reaction, addition reaction. It's an addition reaction, and that addition reaction occurs like this, and after addition reaction we'll get our that intermediate compound that is the ozonide. Now this ozonide on reductive cleavage gives us what? Yes, carbonyl compound. Okay, so we got the mechanism of this reaction. It's a very simple mechanism known as what? Reaction. That reaction is known as ozonolysis reaction. Okay, yes. So as I mentioned at the start of my lecture, that in this lecture I'm to tell you some tricks regarding ozonolysis reaction, or how to identify the product of ozonolysis reaction in a single step. Okay, so let me clear it. Now this reaction, you'll find this ozonolysis reaction in MCQs like an organic compound with particular molecular formula, which they are going to label as A on a reaction with something gives B, B on reaction with something gives C, C on reaction with ozonolysis gives particular compounds. What is ABCD, or what is the that original compound? Okay, so let's see that trick. So before I will explain that trick, or I will tell that trick, let me tell you here first of all some points regarding same reaction. Okay, let's talk about symmetry of alkene. Symmetry of alkene. So here I'm taking some examples. CH3, then CH, double bond, CH2, CH2. Then two isomers of butene, which are CH3, then CH, double bond, CH, single bond, CH3. Its isomer is a CH3, then CH2, then CH, double bond, CH2, CH2, then CH3, then C, then CH3, then double bond C, then CH3, and then CH. Okay, and so on and so on. So these are some examples of what alkenes. So it is a ethene or ethylene. This alkene is called propene, right? Yes. Now this alkene is a butene. It's a 2-butene or butene. Next one is the its position isomer, that is but1ene or 1-butene also. And the next one is the dimethyl derivative of what? This compound. Okay, so 1, 2, 3, 4. So parent alkene is once again same. It's a butene, that is but2ene, and two methyl branches are present on second and third carbon from any ends here, 1, 2, 3, and 1, 2, 3. So the position of all the locants for these two methyl branches remains same, so you can start numbering from any end. So if I have this straight chain as a long chain, then on second and third carbon atom I can find two branches which are like branches, identical branches. So we use the prefix di. So along with two locants, it becomes 2,3-dimethyl. It's a butene. Correct? It's a 2,3-dimethyl butene. So let's talk about symmetry of what alkene. How to check symmetry of alkene? Or to check the substituents present on that two unsaturated carbon atoms, right? So here these two are the carbon atom. It's a simple alkene or simplest alkene called ethene or ethylene. Now these two are the unsaturated carbon because double bond is present between these two carbon atoms. So we can call these two carbon as a unsaturated carbon. And if we check the substituents of these two carbon, then this carbon carry two hydrogen atom. Likewise, this carbon also carry two hydrogen atom. So as the substituents present on these two carbon are same, so it clearly indicates that this alkene is a symmetrical alkene. Got it? Yes. Now let us check symmetry of this alkene. Now this alkene is a propene or propylene. Now these two are the carbon atoms. In between there is a double bond. So these two are, we can call these two carbon as unsaturated carbon atoms, right? So let's check the substituents of these two carbon. Now this carbon, let me split it. Let me split this structure. H and then H, and this carbon also carrying one H. So here this carbon carry this hydrogen and this methyl as a substituents, right? And this carbon carry two hydrogen atoms as the substituents. So are they same or different? Yes, they are different. Means the substituents present on these two carbon atoms are not same. Therefore, this alkene becomes what? Unsymmetrical alkene. Got it? Unsymmetrical alkene. If you check similarly, if you check the symmetry of this alkene, then this carbon carry one hydrogen and one methyl group. Similarly, this carbon carry one hydrogen and one methyl group. So the substituents on these two carbon atoms are same, meaning that alkene is a symmetrical alkene, that is but2ene. So but2ene is a symmetrical alkene. And let us have this alkene called but1ene. So these two are the carbon atom. In between there is a double bond. So the substituents of this carbon atom are hydrogen and ethyl group, and the substituents of this carbon atom are two hydrogen atoms. So again, they are not same, they are different, meaning this alkene is a unsymmetrical alkene. Yes. Let's check the symmetry of this alkene. Now here these two are the carbon atom which carry, this carbon carry two methyl groups. Similarly, this carbon also carry two methyl group, meaning it's a symmetrical alkene. Got it? Yes, so it's about symmetry of alkene. Now, why we need this symmetry? Because we can apply the tricks only when we are in a position to predict whether the given alkene is symmetrical or not. Okay. Likewise, if I have this alkene, that is this double bond means what? Here is a CH2. So to check symmetry across this carbon double bond. Okay, so here cyclic compound is present on this carbon, and here this carbon carry two hydrogen atoms, so they are not same, meaning this alkene is also unsymmetrical alkene. Got it? Yes. Now let's see the trick, how to identify the product of ozonolysis reaction or vice versa. CH2, let's start from simple alkene. CH2 double bond CH2. It's a well-known alkene called ethene. If you find question like this at MCQ level, O3 oblique H2O, they will not give you any solvent. Okay, normally solvents and temperature condition in most of the cases. In typical cases, you'll find that temperature conditions, pressure, etc. But in many of the cases, you'll not find that solvent on arrow. You'll be supplied with only reagent. Okay, so it's a reagent, meaning with the help of this, you have to first of all You must be position. You must be there in position to identify the type of reaction. So if you find this type of condition on arrow, then it clearly indicates that it's a ozonolysis reaction. Okay, right. And it's not like this. O3, and here suppose if I write here Zn oblique H2, not only H2, Zn oblique H2. So it's the first condition, it's the second condition. Means you have to identify the final product. Okay, so it clearly indicates that reaction occurs in a two-step. So first step is the addition of ozone. It's the addition of ozone which gives us that ozonide. And second cleavage is reductive cleavage because it's a reducing agent. Okay. Now in some cases we may find here H2O2. H2O2. So if H2O2 is here instead of Zn and H2O, then that will indicate what oxidative cleavage. Products are different. Okay. Reductive cleavage gives one type of product and oxidative cleavage gives another type of product. So we'll see that later on. So let's see first of all reductive cleavage. Here, how to identify product? We just break this carbon-carbon double bond like this at the middle. Okay. How many total number of oxidants are present in ozone? Yes, three. We give one oxygen to this carbon and other oxygen to this carbon, and forget about third oxygen. Actually, that is going to couple with what zinc, giving zinc oxide, which on decomposition by water uses what zinc hydroxide. They will not ask you secondary product. Okay. They will ask the major product of the reaction. What is the product of this reaction? What is the product of this reaction? That is final product, not ozonide. Yes. So this becomes CH2 and O. Actually, this O is doubly bonded with this carbon. Means we want to break this bond. We want to break this bond exactly at the middle. Okay. Bond break means what? हमें यहाँ पे क्या करना है? Double bond as it is रखना है. Double bond as it is. And double bond को हम क्या करेंगे? Double bond को oxygen के साथ जोड़ देंगे. So carbon will be doubly bonded with this oxygen. Similarly, ये कार्बन जो है ना, ये भी इस ऑक्सीजन के साथ डबल बॉन्ड फॉर्म करेगा. मतलब हमें यहाँ पे क्या मिलेगा? CH2 डबल बॉन्ड O और यहाँ से भी CH2 डबल बॉन्ड O. मतलब HC डबल बॉन्ड O and H. That is HC double bond O and H. CH2O. That is formaldehyde. So you get H. I'm writing a splitted form of the compound HC double bond OH. You'll get two molecules of same compound. Yes, why two molecules of same compound? Because alkene is symmetrical. You get my point? So whenever alkene is symmetrical, then that alkene on ozonolysis followed by reductive cleavage gives us what? Two molecules of same carbonyl compound. And in this case, we're getting two molecules of what? Formaldehyde. That is the point. Forget about secondary product. Okay. Now this HC double bond OH, that is nothing but what? Yes, that is nothing but CH2O, CH2O, CH2O. And the compound is called, it's a methanol. It's a methanol, not methanol, it's a methanol. That is formaldehyde. Its common name, its trivial name is a formaldehyde. So it's a formaldehyde. What is it? Yes. Now let us solve this alkene. This alkene, CH3, then CH double bond CH2. Okay. On same reaction, that is ozonolysis followed by reductive cleavage followed by same reductive cleavage. Breaking takes place across carbon-carbon bond. Give one oxygen to this left carbon, other to right carbon. So this becomes CH3, CHO. CHO means aldehyde group, right? And from this side we'll get CH2, that is same formaldehyde. So in this case we'll get two different aldehydes. So first one is CH3, then C double bond O and H, plus second one is the HC double bond O and H. So one is the acetaldehyde. What is this? It's the acetaldehyde, acetaldehyde. It's the acetaldehyde, and the other one is same. It's a formaldehyde. It is formaldehyde, right? Okay. So why we're getting two different molecules of carbonyl compound? Correct, because alkene is not symmetrical. It's a unsymmetrical. So whenever unsymmetrical alkene is there, then that on ozonolysis always gives two different carbonyl compound. And when symmetrical alkene is there, then that on ozonolysis always gives two molecules of same carbonyl compound. Let us have one more example. Suppose if I use here this CH3, then C, then CH3, then double bond C, then CH3, then CH3. And if they give you this type of condition, same, that is, then reaction becomes ozonolysis reaction. Okay. So breaking takes place across this carbon-carbon double bond. Now first of all, you check symmetry of this alkene. Symmetrical or unsymmetrical? Yes, it's a symmetrical alkene because the substituents of these two unsaturated carbon atoms are Same. So give one oxygen to left, other to right, and form double bond between this carbon and oxygen. So C will be doubly bonded with this oxygen, or O will be doubly bonded with this carbon, and here also same. C will be doubly bonded with oxygen. So we'll get CH3, C double bond O, and then single bond CH3. So we'll get CH3, C double bond O, and then CH3. As alkene is symmetrical, so we'll get two molecules of same carbonyl compound. So now this compound is known as what? Yes, it is called acetone, dimethyl ketone. That is propanone. Propanone is the IUPAC name. Got it? Yes. Let's have a couple of more examples so that we can get better idea about this trick, which is how to identify the product of ozonolysis reaction directly or in a single step. Now, if I use this alkene, if this is an alkene, then on ozonolysis reaction, that is O3 followed by reductive cleavage Zn and H2, Zn and H2. A breaking takes place across carbon-carbon double bond. Okay, give one oxygen to this carbon. Okay, I mean join one oxygen to this carbon through double bond or by double bond. Similarly, another oxygen to this carbon. Here this carbon carry 2H. It's a CH2. It's a bond line formula for alkene called 1, 2, 3, 4. It's a but 1. So the product, what about symmetry of this alkene? Symmetrical or unsymmetrical? Yes, it's unsymmetrical alkene. So, because here the substituents of these two carbon atoms are not same. Here this carbon carry 2H and this carbon carry 1H and one ethyl group. It's a ethyl group. Okay. So you'll get this type of structure. CH3, this CH3, then CH2, then here is a C, this C, which will be doubly bonded with this oxygen. So I'm putting that double bond over here, double bond H, and don't forget that this carbon carry one hydrogen. So it's a dash H, 1, 2, 3, 1, 2, 3. So propane, propanol. We'll get what? Propanol. That is propione aldehyde. We'll get propione aldehyde, propione followed by aldehyde. That is propione aldehyde, and plus you'll get from right hand side you'll get formaldehyde, that is H, then C double bond O and H C double bond O and H. So that is formaldehyde. Got it? Now if I use, or if I have this alkene, now this alkene is called what? Correct. It is called cyclohexene. Cyclohexene. So breaking takes place across this carbon double bond, one oxygen over here, other over here, and here is the H, here is also H. So we'll get, after ozonolysis reaction, we'll get this type of compound. Then dash C double bond O and H, and here also dash C double bond O and H. Correct? 1, 2, 3, 4, 5, 6. It's a hexane diol. What is this? It's a hexane diol. So it's a product of this reaction. Ready? Yes. Now suppose if I ask you one question like an alkene on ozonolysis gives 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 mm, acetaldehyde, mixture of acetaldehyde and propionaldehyde. Then what will be the structure of alkene, or what will be the alkene? Okay, an alkene on ozonolysis, or question like this: which among the following alkene on ozonolysis gives mixture of these two, that is acetaldehyde and propionaldehyde? So it's a reverse question. Okay, so don't worry about it. It's a very simple one. So first of all, you have to draw the structure of these two compounds. One is acetaldehyde, so that is CH3, then C, so CH3, then C, double bond O, and then H. Okay, you put two carbonyl groups of both the aldehydes, or even ketone. If ketone is there, then that ketonic group will be there. So this oxygen atom must be present in front of each other. So double bond C, then CH2, and then CH3, and here is a H. So it's a propionaldehyde. Okay. Then remove these two oxygen atom and extend these two bonds. So when we extend these two bonds, then we'll get structure of that alkene. Right. So what is this? CH3, then CH. It's a double bond. So its length is quite more. Then CH, single bond CH2 followed by CH3. So it's a 1, 2, 3, 4, and 5. So it's a pentene. It's a pent 2-ene. What is this? Pent 2-ene. Got it? Yes. Then one more point, that is an alkene on ozonolysis gives acetone only. Okay. So which among the following alkene on ozonolysis gives acetone only? Only means what? Look at only acetone after ozonolysis reaction. So it clearly indicates that the alkene is a symmetrical alkene, right? Yes. So like 100.2 structures of what is acetone molecule, that is C double bond O and then CH3 and then CH3. Okay, just put carbonyl groups of two carbon atoms, two molecules in front of each other. So it's a carbonyl of this one acetone molecule. Similarly, one more acetone molecule C, then CH3, then CH3, and then double bond O. Remove these two oxygen and extend these two bonds. So you get structure of alkene. So what is this? One, two, three, four. It's a butene, that is butene. Then on second and third carbon, two like branches are present. So locands are 2 and 3. Prefix will be di, so 2,3 dimethyl or dimethyl butene. Okay, so this must be alkene. On ozonolysis gives us what? Acid. You can check it. You can check it. If I carry out ozonolysis of this compound, this alkene, then one oxygen on left, other on the right. So this oxygen will be over here. This oxygen will be over here. Okay. So what is the carbonyl compound? It's acetone. It's acetone. Acetone only because alkene is symmetrical. That's why. Got it? Yes. So hope you got some idea about tricks. I mean, how to identify the products of ozonolysis reaction. Okay, as well as the mechanism. Mechanism is very interesting mechanism. So it's all about this mechanism and some tricks of ozonolysis reaction. Okay. So if you like my channel, then please subscribe it and share it with your friends. And don't forget to put comments if any, so that if any queries are there, I can improve myself. So yes, bye. Take care.